We welcome you all to our webinar this evening. The title of the webinar this evening is Managing Uncertainties of the Future Grid. We have one keynote speaker for tonight in the person of Professor Jay Giri, and I'll be your host and moderator for this webinar. Just a few housekeeping issues. Attendees are reminded to turn on their volume and ensure that you have a stable internet connection to enjoy the webinar this evening. A record of the webinar will be available on SAIEE TV on YouTube. A certificate of attendance will be issued once we have received CPD validation from EXA. Thank you very much for joining us, and we believe that you will enjoy the discussion this evening. My name is David Oyedokun. I currently chair IEEE South Africa section, and I have served the IEEE in a number of roles over the last decade or thereabout. I'm a senior lecturer at the University of Cape Town. My area of specialization is in power systems with interest in renewable energy as well as geomagnetically induced currents. Our host for this evening is myself, as I've mentioned. At this point, I'll be taking you through who our keynote speaker is. Professor Jay Giri is an independent consultant with GGM Consulting, a sole proprietorship. He retired in July 2017 as Director of Power Systems Technology and Strategic Initiatives at GE Grid Software Solutions in Redmond, Washington, that's in the United States, where he managed a team of power system engineers who delivered generation control, market applications, and synchro phaser measurement unit, PMU, applications to control centers. He was also the corporate liaison for university research activities. He is an affiliate professor at the University of Washington. In 1978, Jay and 11 other engineers co-founded Energy System Computer Applications. Over time, ESCA became Alstom Grid in 2010 and GE Grid Solutions in 2015. Professor Giri designed and implemented the original software for the ESCA, Automatic Generation Control AGC, and Dispatcher Training Simulator DTS, Power System Simulation functions. Today, this AGC controls over 50% of North American generation, as well as generation in many other countries. And the DTS is one of the predominant simulators used by control centers worldwide. I welcome Professor Jay Giri. I'll now make him presenter, and he will take us through his presentation.
Thank you, David. Can you hear me okay?
100%.
Very good. Okay, so I really appreciate this opportunity to join you. I remember being there 3 or 4 years ago where you hosted me for a week in different cities in South Africa, and it was one of the highlights of my career. I mean, it was an amazing trip. So today what I'm going to talk about is managing uncertainties in the future grid. Give you a little bit of a sort of historical perspective, how we got here, and then how some of the new technologies, the synchrophaser analytics, is sort of helping us solve these new challenges. So with that, the first, I've broken it into 2 parts. The first one is I'll talk about electric power grid, real-time grid management, which I just call RTGM for, and energy management systems, which is the common term for EMS. And So the electricity supply chain, this is the power grid since its inception many, many years ago. You start off with the generating station at low voltage, you step up the voltage, send it across long distances using the transmission system, bring it down to the lower voltages at the distribution system, and then at even lower voltages, safer voltages for the customers. So the traditional model has been that electricity flows from generation to the customers, and the revenue flows from the customers to the generation. So this is the way we've been operating the power grid. So in 2001, the National Academy of Engineers sort of polled all the engineers, electrical, mechanical, civil, etc., and asked them what they felt was the greatest engineering achievement of the past century. This was in 2001. And the consensus was electrification was the most significant engineering achievement, which really is the foundation of society in many ways. And so I'm very pleased to have spent 40 years of my career working in electrification and trying to keep the power on to customers. Okay, the grid began over 125 years ago, a small entity in New York City. Thomas Edison was involved, and it consisted of just a few pieces of equipment. Today, it consists of many millions of pieces of various diverse grid components, and it is one of the most complex and immense must-run engineering machines in existence today. So it has to run around the clock, and you've got millions of pieces of equipment which have to be working in unison successfully in order to provide electricity from the generators to the customers. So the challenge we face is electricity demand changes second by second. Anytime someone turns the light switch on or off, the demand has changed. The other problem is electricity cannot be stored easily, unlike other energy resources like oil and gas, where you can have big storage facilities which you can draw upon as you need it. Electricity today does not have an affordable, large-scale, grid-level storage capability that we can deploy easily. I mean, there are some solutions, but none of them of the level that we need. So the problem is, if supply does not meet demand, meaning demand is changing all the time, and if generation cannot meet demand, then frequency will deviate from normal, and protective relays will trip, and it could lead to a potential widespread cascading blackout. So the issue is supply needs to meet demand immediately. Immediately meaning as soon as supply demand changes, generation needs to respond and provide for that demand change immediately. So the grid operating paradigm over the past 125 years since its inception has been that generation resources must react immediately to follow changes in load, or essentially what we call generation follows load. Now, the reason I'm emphasizing this is because later I'll explain why this paradigm is shifting. Now, the major sources of grid vulnerability are this list here: natural calamities, which are getting worse. Whether you believe in climate change or not, I mean, we are seeing situations which we've never seen before in terms of superstorms and hurricanes, etc. Line overloads and equipment and protection failures. I mean, a lot of the equipment is very old and beginning to fail. Communication failures, faults, human errors, inadequate security margin, and in places where you have the electricity market, you have gaming and etc. So these are the major problems that we face in trying to manage the grid. So the reality we face is our grid is too complex to make it fail-safe. It consists of millions of pieces of equipment, and all it takes is a few pieces to fail, and you have a problem. So blackouts will occur again in the future, and that is something we have to face. So what is the solution we seek? So we want to contain grid disturbances quickly to avoid a cascading failure of the grid. Now, grid disturbance are occurring every second. I mean, each time you turn a light switch on or off, you've created a small disturbance. Each time a transmission line goes out, that's a major disturbance. So the solution we're looking at is to be able to identify the disturbance and to quickly contain it so that it doesn't propagate. And the other aspect is, how can we restore power to customers more quickly? Because if we say that blackouts will occur, the next step is how to get power back to the customers. And as you and I know, if we can restore power in 5 to 15 minutes, people are not inconvenienced as much. But if it's a few hours or a few days, then it's a major inconvenience. And so another area which I wish we spend more time on research-wise is doing restoration, how to quickly restore power to customers. Now, the real-time grid management landscape consists of various different drivers and priorities, but the key operation priorities to keep the lights on are reliability, meaning make sure that every customer who wants electricity gets it. Security, meaning that if there is a disturbance or an outage on the grid, can we survive it and still supply electricity to the customer? This is also called like N-1 contingency studies. And efficiency, basically saying that can I supply electricity to the customers at the least cost? So these have been the three operation priorities that were driving us building solutions for real-time grid management. And this is what I was involved in when I started 40 years ago. So let's talk about the energy management system. And the big bang which created the energy management system was the 1965 blackout in the Northeast US. Lasted over 13 hours, 30 million people, billions of dollars in lost business, and a wake-up call to the US public. Because up until then, the customers just assumed that electricity was like water in the US, where anytime you wanted it, you got it. But that was a wake-up call for them. So after 65, the public outcry said, we don't want to see this again if we can. And so people started spending time and money on innovative blackout prevention solutions and trying to make sure that this kind of a situation didn't happen again. And we were very lucky at that time. It was a fortunate nexus of three things: greater R&D funding for power systems. I mean, that's how I got into EE electric power systems, because I knew that there were some new challenges which are exciting. More students, electric power engineering, and the birth of affordable digital computers. So we started getting computers which were able to solve complex problems more easily. And that resulted in the development of the modern EMS using digital computers. So the energy management system has been evolving over the past 50 years. The goal is to manage the physical flow of electricity, operate the grid within safe limits, prevent blackouts, adjust generation to demand, identify risk, and take preventive actions and expedite restoration. So those are the things which the EMS objectives are, and you have operators and engineers supporting this objective. So this is what a modern EMS control center looks like. It consists of various large screens on the wall, which allow people to look at a wide area view of what's happening on your grid. And you have different consoles where you have different operators with designated functions, like it could be switching or interchange scheduling with your neighbors or whatever. And then you have a supervisor who's sort of coordinating all the activities. So the software which drives the EMS, and this is what I've been involved in since 1975, 78, consists of various subsystems. Okay, obviously you have the operating system or the digital computer, then you have a database and development environment, and SCADA, which is supervisory control and data acquisition, which is one of the first functions which existed. Then you have generation applications, transmission, a training simulator. Then you have study and analysis modes. And you have operator consoles which interact with these. So these are the operator functions which the operator interacts with these kinds of functions. And the engineers operate, the software and IT people deal with this. And essentially, you're getting measurements from the power system, all the high voltage substations, through a communications network, data acquisition and controls, which comes into SCADA. So if SCADA fails or this communication system fails, basically the EMS is not able to perform because it's lost its connection to the grid. So SCADA is vital. So the EMS operator's objectives are reliability, making sure every customer gets the electricity that they desire, and economics, to provide it at the least cost. But obviously, reliability always trumps economics, meaning that if push comes to shove, you will sacrifice economics to make sure reliability is maintained. So this is an analogy which I use to try to explain what the EMS operator's objective is. The objective is to drive the car and stay on the road. And you can only use the dashboard, which means all the current conditions which are happening on the system, and possibly a rear view mirror, see what has happened in the immediate past. So these could be strip chart recorders or trends or whatever. Now, fortunately, in the days before yesterday, we had plenty of room on the sides of the road, and you had plenty of, it was a relatively straight road with plenty of margin on either side. But today that's changing. Okay, so today the operator's role is getting more difficult because there are tighter margins and the road is beginning to sort of not be as straight as it used to be before. So the challenges are greater. So the main EMS operator applications are SCADA, which runs every 2 to 4 seconds, retrieving data from the grid. Now, you do not know when that measurement was made because it could have been made a few seconds ago or a few minutes ago, but you bring it into the control center every 2 to 4 seconds. And also from SCADA is the only place where you can perform manual supervisory control actions. You can trip circuit breakers or things, change tap settings, etc. And these are done remotely from the control center. Generation scheduling and dispatch, your load forecasting, scheduling, AGC, automatic generation control. I consider this one of the first smart grid applications that was built in the 70s. And the objective is to ensure that generation load balance is maintained second by second. So this is the only closed loop function in the control center, meaning that it's like an assistant to the operator, where it senses generation load imbalance and immediately sends controls to the generators to sort of bring it back to balance. Then we have the transmission grid management system, state estimation, contingency analysis. Like I said, this is security analysis and optimization, volt-var control, and loss minimization. So in fact, we could spend a week on each one of these topics to talk about the technologies involved and how these applications work. So these are the functions which the EMS operator interacts with. These are the EMS operator functions: SCADA, network, generation. But we cannot forget the infrastructure functions, which are the foundation upon which these rely. You have system functions, communications, real-time database, user interface, system modeling, intercontrol center communication, and etc., archival, etc. So what we have are millions of lines of code at rates of seconds and minutes, which have to run successfully around the clock. It's a pretty daunting task, but we have done it. Now, the EMS views of the grid are, like I said, SCADA, AGC, secure network analysis, and the training simulator. And if this is your utility, you own this piece of the grid. So typically, a grid consists of a number of utilities in the interconnection, but you only have real control over your own utility. So RTUs, or remote terminal units, bring data back from your system to SCADA, And these are asynchronous, uncorrelated, and I call this a telemetry view. Then we also have the energy balance view, where you're looking at generation load imbalance, and in order to make sure frequency stays close to normal, and that's done by AGC. Then you have a grid network model, which is a correlated view, and there you look at your utility as well as the neighboring grid, because when you have a disturbance on your utility, electricity can flow through your neighboring grid. So you have to model any relevant portions of your neighbors which affect your grid. And then you can look at future scenarios, what is coming up next, meaning you can run look-ahead simulations to say what is happening, or you can also look at past scenarios and recreating them. And that's where the training simulator comes in. So these are the typical EMS operator displays. You have a system-wide visualization, which shows you little contours of low voltage, if you wish, or different kinds of phenomena occurring on the grid, or you can look at weather patterns coming across and be alert to that. We also can commingle geographical displays with SCADA displays. This is your typical SCADA display, which has been in existence for 50 years. And essentially what it is, the little red squares are circuit breakers. And from the SCADA display, an operator can go in and open or close a circuit breaker by a multi-step procedure. You select and you say what you want to do, and then you execute. So you want to have a multi-step procedure because you want to make sure you don't inadvertently open or close the circuit breaker. Then you can also look at little tabular displays of voltages, etc., and look at low voltage areas in the grid. Now, this is another view of voltage problems and solutions. So here an operator would see that the orange means that I have a low voltage situation. And then we can run analytics, something like VSAT, voltage stability analysis, and recommend that if you increase your reactive resources in these magenta areas, you can solve the problem. So one thing to remember is the grid operator does not just want to know that there is a problem unless they can fix it. So if you tell a grid operator that your system is going to collapse in the next 30 minutes, the first question is, how can I avoid that? And if you say, I don't know, then the grid operator will say, why are you telling me? So you have to provide information to the grid to fix the problem. So this is an example of how you can provide information to the grid of fixing problems. Say you have a low voltage situation over here. Now we have a tool where you can use your cursor and actually go and freehand lasso an area and say, show me all my reactive resources in that area, which will allow me to fix the problem. So it shows you the units, capacitors, reactors, SVS in the area. And now the operator has the ability to either call up a substation operator or switch in a capacitor in order to fix the problem. So I want to emphasize that the operator wants actionable information, something that they can do to fix things rather than just be aware of things. Okay, the evolution trends. When we started, 89 1200 buses at Pennsylvania Power and Light was considered a large model. And this is limited by the hardware capabilities. I mean, what can the computer handle? I mean, can we run AGC in real time? Can we run state estimator in a minute, contingency analysis in a minute, etc.? And then over time, you can see that we've been blessed with the fact that the hardware has become faster and faster and more economical, so that we can distribute computing and handle much larger systems. So in 2004, I remember it was the MISO system, which was 32,000 buses, which is almost unheard of. And today, from what I understand, that the MISO model has grown to over 40,000 buses, and it's solving state estimator every minute or so, and solving contingency analysis of thousands of contingencies in a matter of minutes. It's quite mind-boggling. So the problem is As you get to larger model sizes, the operators are inundated with data, and they really don't want to figure out what's happening in the 40,000 buses across the grid. And what they really want to know is actionable information. So part of the challenge now for the EMS is not just to display things from the grid, but to use intelligence to synthesize the data and only present data like in a pop-up manner to the operator to say, you better look at this area because this needs attention in order to protect the overall grid. So today's grid is already smart. I mean, people talk about the smart grid, and I think it's already smart in many ways. We have system-wide smarts, we have EMS operator actions, AGC, which is running continuously every 4 to 10 seconds. We have load shedding, under and over voltage and frequency load shedding, and special grid protection schemes like RAS, remedial action, and system integrated protection, integrity protection schemes. And we have regional smarts for volt var control and voltage load shedding. Now, voltage is more of a local phenomena, so you can fix the voltage problem locally. But for system-wide, it's more frequency, which is a system phenomena. And then you have equipment smarts, meaning any piece of valuable critical equipment on the power grid has a relay which is used to protect it, to make sure it's not damaged or under emergency conditions. So the grid is already smart at various levels. So to summarize the first part, the power grid is the most complex, immense, must-run machine. Today's grid is smart, but changes are afoot, and imminent, unprecedented changes mean that tomorrow's grid needs to be even smarter. So the next part, I want to focus on synchrophaser technology, phasor measurement units, PMU benefits in the EMS, and future grid challenges and solutions. And also, I want to close with some thoughts on the impacts of COVID-19 on grid operations. So the current challenges are an aging grid and retiring workforce. I mean, I'm an example of the retiring workforce. We all started 40 years ago when it was the exciting thing to be in power systems in the late 60s and early 70s. And many of us are retiring right now. In most of the developed countries, the grid is aging. Many of the pieces of equipment are well past its life cycle. But in other countries like India and China, a lot of the grid is new, so they don't have this problem. Cybersecurity, our systems are being constantly hacked, whether we like it or not. People are trying to get into the EMS in order to, I don't know, do what, maybe try to trip a breaker. IT architecture, communication services are becoming more important. I mean, because we have to have protection against hackers. Business models, we get new regulations from the government and a renewable portfolio standard saying that you must have 20% renewable by so-and-so date. And so we have to look at how to do that. Grid instability, as you have electricity markets, people want to maximize the utilization of the transmission grid. So that leads to operating closer to the limit, which creates instability issues. Scalability, I mean, the software needs to be able to handle the MISOs, the 45,000 buses, or a microgrid, which consists of 10 buses. And most vendors, fortunately, have software which is scalable. You just have to compile it overnight, and you can have an EMS for 10 buses or for 45,000 buses. It's the same software. Superstorms increasing, hurricanes, sustainability. There's a great push for carbon-free renewables and microgrids, efficiency, distributed energy resources, distributed generation, demand response, and more active participation by customers. So these are things that are happening today. So I want to zoom in on one promising technology, which is synchrophaser technology, PMUs. The PMU was built in the early 80s by Professors Fadke and Thorpe. And they really never found the light of day in terms of grid operations until 2009, when the DOE, through the stimulus grants, provided funding to deploy PMUs all across North America. And ever since then, it sort of cascaded into the rest of the world. And many countries are deploying PMUs very aggressively. So what is synchrophasor technology? The synchronous measurements, the voltages, currents, ABC, positive, negative, and zero sequence, frequency and rate of change of frequency, and also some status information. It's higher resolution sub-second scans. Remember, SCADA is every 2 to 4 seconds, and this is every few milliseconds, 30 milliseconds or so. And more importantly, they're all timestamped. So you know precisely when the measurement was taken. And unlike SCADA, which does not have timestamps. So the real-time grid measurements will be much faster. It's an unprecedented transformational change. And Mr. Terry Boston, CEO, used to be CEO of PJM, really pushed a lot of the PMU technology at TVA and PJM. And he compares PMUs to MRI versus X-ray visibility of SCADA. The costs are declining. They used to be more expensive. Installation was more expensive because you needed high-speed communication, but now a lot of the substations have high-speed communication, and the device costs are much less expensive. And we also have other multifunctional devices like relays with GPS and fault recorders, which provide similar information. So the new SCADA frontier for EMS is, this is the way SCADA has evolved over the past 40 years. Every 2 to 5 seconds, latency and skew, older communication. And a frequency change means there's a problem somewhere in the grid. It may not be in your system, but it's somewhere in the interconnection. And the phasor data of the PMU, which is today and tomorrow, the refresh rate is 30 to 60 samples per second, time tagged, compatible and common modern technology response to dynamic behavior, and an angle pair change, a PMU angle pair change means a sudden megawatt change in a specific location in the grid. So earlier information for better decisions. So in my 40 years, this has been the first sort of really significant change in EMS technology, which has helped benefit grid operations, because over the past 40 years, there have been incremental changes, and this is the first step change which will help us. So this is what the EMS with PMU analytics looks like. This is the traditional EMS with uses a network model for your state estimator and all these other functions. And here you have the PMU analytics, which do not need a network model because the grid is your model, is getting measurements. And these are analytics which are developed using just the digital signal processing and getting data out of this data stream. And so you have wide area monitoring systems, state measurement, oscillation monitoring, etc. And the PDC is the phasor data concentrator, which brings in the PMU either in here or into the traditional. So PMU visualization, angular separation is an indicator of grid stress. If the PMU angle between any 2 points suddenly changes, either the transmission path loading has changed or the topology of the grid between the two has changed. So if the angle increases, that means the megawatts may have increased, or you may have lost the transmission line between those 2 points. The grid has weakened. So just measuring the angle difference between any 2 points is a very valuable indicator of problems in the grid. So this is an example of if we had PMUs in August 14th, 2003, if we had a PMU at Cleveland and one in West Michigan, and if you monitored the angles difference between the two, you would have noticed that the angle difference kept increasing over time. And eventually it led to collapse. So the thing was, we had an hour to react, analyze, and mitigate this issue. So all it would have taken is for a Cleveland person to call with West Michigan and say, hey, what's happening? We're drifting apart. And they could have looked into it and tried to take corrective action, either through changing schedules or even, in the worst case, shedding load. So Stability management is something we can do with PMUs. We can extract the frequency, the amplitude, the decay time, and the phase. All these are nice to have, but this is the critical piece of information. If most of the oscillations which occur on the grid decay quickly, I mean, like I said, disturbances are occurring on the grid second by second, and all of them are well damped and disappear. But occasionally you may have an oscillation which is not damped, meaning it increases over time. And that is the one we need to look at and alert the operator and say, what can we do to avert that from continuing? Stability assessment, again, in the past, it used to take many minutes to do this, but today we can do it very fast with PMUs. Disturbance location, this is a really nice example. I mean, this is originally Professor Yilu from Virginia Tech who developed this technology originally. And it's like dropping a pebble in the pond over here, and you see the frequency sort of distribution across the grid as it propagates across the grid. And using this propagation, you can sort of triangulate and say that this is where the disturbance occurred. So, like I said, the operator wants to know when a disturbance occurs, where did it occur, and what can I do about it? And so this is a really valuable piece because it may not be in your system, but it could be in your neighboring system. But you can quickly tell by just looking at the PMU patterns, measuring frequency, where the disturbance occurred. And also islanding, you can look at situations where you've suddenly islanded. I know this doesn't happen very often, but with the traditional EMS, it would take you many minutes to say, this is where we islanded, this is where the lines are affected. But with the PMUs, within a matter of a second, you know exactly where the island is. This is sort of coherent, and this is the second island. So it's a much faster sort of visualization or awareness of happenings on the grid. So these are some of the new PMU analytics in the EMS, and this is in the millisecond to second time frame. And angle pair monitoring, oscillation detection, etc. And then these are some of the new ones which are being developed by researchers, which we need to get online quickly. This is integrating fast control devices with PMUs and real-time transient stability monitoring. PMUs also benefit traditional EMS and RT real-time grid management, and this is in the seconds to minutes time frame. SCADA, you can enhance real-time monitoring. AGC, you can minimize unnecessary controls. And these are people are doing this, they're enhancing AGC with PMUs. State estimator, of course, the state estimator calculates voltages and angles, and PMUs give you the voltage and angles. So if you had PMUs at every substation, you really have a state measurement rather than a state estimator. You can improve EMS model data. I mean, a lot of our EMS models have impedances, which are defined from whatever your books, your Westinghouse T&D book. But now with PMUs, you just put a PMU at two ends of a line. You have voltage and current here, voltage and current here. You know exactly what the impedance is because they're time synchronized. So you can monitor impedances over time. And all these other things which can benefit with PMUs in existing capabilities in the EMS. So quickly, some practical deployments. Wide area monitoring systems, or WAMs as they're called. I mean, this is a picture from 2016, which shows where they have been deployed across the world. And no doubt, a lot of these do not have an active role in decision making yet, and they're in the engineers' purview. They're looking at it, but there's no active decision making being made other than without having an engineering person in the loop. But you can see that's being tried in different places, and the Go 15 or the 100 gigawatt customers are also involved in this. You have MISO, you have ESCOM, you have India, France, etc., Korea. So a quick look at what India has done, because it's something we were involved in, and we're very proud of what has been accomplished over there. India's grid evolution since the 60s, it's operated as 5 regions, Northeast, etc. In 2013, they connected the southern region, and so it became one nation, one grid, and one frequency. And today, the Indian power system, one of the largest synchronous grids in the world, and probably the Chinese, not China grid is equally large. So a recent project which was implemented in India after the 2012 blackout that they had over there, they wanted better visibility, was deploying PMUs all across the country, 26 states, 5 regions, 359 substations. So now if you go to the National Control Center in Delhi, you will see measurements coming in at a sub-second rate and showing you the entire country and the voltages and angles across. It's one of the world's largest VAMS projects. Okay, so now if we shift gears and look at future grid management. Okay, I'll try to wrap up in another 10, 15 minutes. We have increasing uncertainties, challenges, and I'll talk about some solutions. So this is the future grid uncertainties, challenges, and opportunities. And some of the new ones are handling big data. PMUs are providing, generating terabytes and petabytes of data. We also have automated meter systems which are bringing in voluminous data into the control center. So what do we do with it? How do we utilize it and mine it for information? And also some of the impacts of cloud computing and blockchain. How can we apply some of this? There's some opportunities to apply that to helping grid operations. Now with the big data, I mean, obviously you have much larger volumes of data coming across communication channels. So cybersecurity becomes even more important than it was before, because all it takes is for a hacker to go in and hack and bias some of the data. And if you're using it for decisions, like in the future, that could be a big problem. Sustainability, this is getting obviously a much bigger global look at. Uncertainties are growing, proliferation of carbon-free renewables, electric vehicles growth, active customer involvement. I mean, demand response is one of them, and this is where a customer can say, okay, you can cut off my load for say 15 or 30 minutes when you need to, if you're in an emergency, and then the utility would give them a sort of a break on their bill if they participate. So these are some of the uncertainties, and a lot of it is happening at the lower voltage distribution system. And in the old days, the transmission system used the distribution system as a pass through to the customer. It was just like a one-way, but now the distribution system is getting more active, and so the transmission system is being affected in ways it wasn't before. Okay, so that's the more active and intelligent distribution system. So today's operation priorities, which have the traditional reliability, security, efficiency, but some of the new priorities we're looking at in grid operations is flexibility and resilience. So resilience is the ability to anticipate and prepare for potential disruptive events. So this is from NERC. It says an event occurs and you try to mitigate it and try to bring it back. So how resilient is it to make sure it stops getting worse? Reduce the magnitude and duration, adapt function, and rapidly recover. So reduce magnitude of a disruption and recover. So that's resilience. Flexibility is the ability to accommodate new entities and programs into the electricity supply chain, DER, proactive customers, etc. Like I said, a lot of this is happening at the distribution or low voltage level. Now, this is a nice good news, bad news thing. Like the good news of renewables is it's carbon-free, it's economical, and this is what situation, this is the duck curve from California ISO, and you can look this up. And they projected in 2013 that this is what my demand is, my daily load curve, and they had the solar, rooftop solar plan where a lot of residences could install, were provided incentives to install rooftop solar, and they predicted that by 2015 demand during the day when the sun is shining would drop, and then 2020 it would drop to here. And I think they reached this 2020 sort of low demand much earlier than that. And the problem is that if the demand goes so low, and then as soon as the sun sets and the sun disappears, now you go back to your traditional generation and say, now ramp up to meet my evening load. And so now the traditional generation has to ramp up at like 13,000 megawatts in 3 hours, as opposed to here, which is about maybe 5,000 or 6,000 megawatts in 3 hours. So that is the bad news. So but if we had storage, and someone estimated, well, if you had 5 gigawatts of storage, then you could build the storage up during this period and then use it during the ramp. So managing the future grid, as Yogi Berra used to say, future ain't what it used to be. And uncertainties are increasing. And they provide challenges and opportunities. The past is not always a good indicator of the future. So that means we have to monitor trends and adapt continually, develop new innovative solutions, leverage new products and technology advances. So the future grid map, the road ahead is much more challenging. I mean, this is just a dramatic view of what it looks like, but really what we need in order to keep the car on the road now is, in addition to the dashboard and rear view mirror, we need to have a windshield forward-looking view. So we need to be able to look at what's coming up and be able to maneuver the car and the grid accordingly. The other thing which I want to mention is you have transmission lines all across the grid, and the power across the line is V1, V2, this equation, plus any HVDC or fax devices that you may have. Now, each one of these in the equation can be controlled by a thyristor control device in sub-seconds. So and these devices are not as expensive as building a new line. So if on major transmission lines you install certain thyristor control devices, you can, during an emergency, invoke them in order to change the power in order to protect the grid. So really you have the opportunity, all this technology exists today, and you could employ this across different transmission lines to make it more ready to respond during an emergency. A quick thing about energy storage solutions, like I said, we do not have really a true grid affordable solution for the grid level, but this is the panacea in many ways. If you had affordable energy storage, you can avoid a lot of the problems and help real-time grid management. Okay, the future electricity supply chain. One scenario is a galaxy of many, many self-sufficient microgrids working synergistically at the lower voltage level. We're seeing a growth of microgrids over time, becoming less dependent on the transmission system. And what that means is that it's possible that you could have a market between microgrids and people being selling in power amongst each other at the lower voltage and with less dependence on the transmission grid. So a lot of the business could be happening here and less depending on the transmission system. So today, the transmission grid is the lifeblood. It's the only electrical source. Tomorrow, it could be the lifeline, meaning that when you need it, then you call upon it, rather like a microgrid. And the business model of the transmission utility will need to adapt. So the future grid operating paradigm is a gradual transition from reactive to proactive. And the reason I say that is that we have demand response programs being deployed where the customer says, reduce my load depending on your generation needs. And this is particularly relevant when you have renewable generation, which you cannot predict, or it could be variable. So you need to have something which buffers us against this variability of the renewable. And if you have loads which respond, that would be an ideal solution. So today we're in a generation following load, but it's quite possible that we gradually move towards tomorrow a load following generation. And this really becomes more important as we increase our renewables and wind and solar, etc., because those are unpredictable and variable. Future grid operation, new automation control schemes, fast sub-second measurements with fast sub-second controls, FACS, HVDC, all these technologies exist today. So we need some intelligence to couple them and to make them work together. And all this happens in a sub-second time frame, so they have to be robust and reliable. Active transmission system, real-time dispatch, and FACS and HVDC, and like I mentioned earlier, and a holistic grid-wide optimization. So looking at all the new entities, storage, DER, DG, renewables, microgrids, someone needs to take a big holistic grid-wide optimization view and come up with a way to engage them. They're all like little puppets on a string, and how do you engage them at the appropriate time to perform the act? Now, this is just a quick, it's a recent project I worked on after retirement, which was related to connecting all the Far Eastern, Far Asian countries in order to share electrons to foster international cooperation. So the thing was the recommendations that put together, and this is available in a report, which I'll give you the reference later, is if we use the regional wide area monitoring system and connected Russia, Mongolia, China, EMS, North and South Korea, and Japan. And really the primary force was, this has been funded by the MacArthur Foundation. And they were looking at how to mitigate the nuclear impacts of North Korea and look for ways in which we can use the nuclear power here for peaceful purposes. And so this was a suggestion I made. We had a nice meeting in Mongolia to end of last year, just before the COVID. And it was presented to all these country representatives, and we'll have to see where it goes next. It was funded by the MacArthur Foundation. Okay, quick few words on COVID, the pandemic. This is obviously a totally unexpected uncertainty. Whoever thought we'd be in this situation as a society? But as far as the grid operations go, electricity demand is lower. Shutdowns have caused a reduction, so that's good in some ways. Daily energy use profile is flatter. Many businesses are shut down, so that we don't have that severe duck curve as I showed earlier. And carbon emissions are lower. I mean, because of reduction in transportation, and people are not commuting to work, and people are saying that you can see the Himalayas in India like you'd never seen them before, because the air is so crystal clear. And as you know, India is in a total shutdown. People are not allowed to leave their houses. Some of the sustaining impacts after the pandemic, whenever that is, hopefully soon, is that we could have an increased focus on automating grid controls to be more resilient. Reduce dependency on large power plants since they're vulnerable to supply chain problems. Like if you have to get parts from China to fix them and you can't do that, then you don't want to be held hostage. Coal plants may gradually decline because load growth is lowered, so maybe natural gas and growth of renewables will be favored. Microgrids, reduction of human contact, I mean, beginning to see that. That's going to be a new norm in society as well as in grid operations. Sequestered operations, staggered work shifts. Use of drones, I can see drones being deployed more widely in the place of people. Leveraging electrified public transportation, electric vehicles, use them as a backup for this electricity grid, and an increased use of cloud-based applications such as for power system simulators and testing. So these are some things which could continue even after the pandemic is over. So with that, I just want to show you just a list of some of the suggested reading. For those people interested in PMUs, this is a wealth of information. I mean, this a lot of utilities and researchers have poured their voluntary time into this organization, and all these reports are available online. You can spend weeks learning about PMUs at this site, and these are some of the other things that I would suggest you, if you're interested, you could look at. So with that, I'd like to thank you, and David, I'll like to turn it back to you.
Thank you very much, Prof. Giri, for for your presentation. The floor is currently open for questions. You are welcome to use the question feature on this webinar application to put through your questions to us, and we will definitely answer the questions. So please don't use the chat function, use the question feature to put through your questions. The first question that we have this evening is with regards to the way renewable energy power generation is centralized. So in the example of South Africa, we have in the Northern Cape, based on solar irradiation, we have a high concentration of solar PV installations, and in the Eastern Cape, we have a relatively high concentration of wind power generation. And if this continues the way it is as it stands today, there's a possibility of network congestion that can happen. A number of countries around the world have seen that, including Italy, Spain, and others. So the question is, in your view, how do you see power system engineers managing the grid in the context of network congestion as a result of the general practice in setting up these renewable energy-based power generating plants?
Yes, so the problem most countries face is the location for the renewables, especially when you're trying to have it in concentrated commercial large-scale plants, is like the wind and solar is typically far away from the load centers. I mean, not very close usually. So you have to build a long extension cord from there to the load center, basically, to bring it in. And now we are vulnerable to that transmission path being a point of failure, which could cause you problems. So really, I don't know what the right answer is. I mean, when we build transmission paths for security, we always build like two double line or 4 lines to make sure that one goes out, that you still have the possibility of the other two supplying the electricity. So we've done that with large hydro plants in the past, like in South America and other places, where you build multiple lines from any critical generation resource in order to ensure security is maximized. So I don't know if that answers your question, but the problem is the other thing with renewables is that they can go on and off at their own whim, meaning that the operators have very little control over them. So one way of mitigating that is if you can have storage installed with the wind. So one solution that I've sort of discussed with people is when you have a renewable resource out in the wilderness somewhere, and if you can couple that with storage and put a PMU on it, then at least the grid operator has some view of what's happening with the renewable, meaning as soon as it goes down, the PMU will indicate that. And then if you can build a control system which will immediately use the storage facility to provide the backup power so that the grid impact is minimized, that would be very welcome by the grid operator. So I think basically security can be built by trying to minimize congestion by building more transmission capability, and then coupling storage and PMUs is another way of increasing the ability to manage the resources for grid operations.
Thank you. I think that answers the question, and I think what really came out there is the role of transmission planning and transmission expansion to ensure that there's room to accommodate these technologies and the change in generation. The next question that we have is, with the increase in players in the renewable energy space, decentralized generation, the question of cybersecurity comes in. So how often are these control centers around the world being exposed to threats as a result of the high number of nodes that are feeding communication through, and the multiple nodes through which the network can become vulnerable.
Okay, like I had mentioned earlier, even before renewables and before PMUs, control centers around the world were constantly being attacked. I mean, the utility companies will not necessarily make a big public statement about it, but we know that people are being trying to get into the software system. And so as EMS vendors, we build firewalls and we build a lot of different things which allow you to prevent people from getting in. Now, renewables per se are not as critical a threat in terms of cyber attacks, in my opinion. But I think things like PMUs and other fast data, which is coming in much faster, I mean, that could be a bigger problem, because when you have a flood of data coming in, and if suddenly someone goes and biases it or changes it, it becomes a lot more of a problem. And again, we need to build tools to analyze and figure out if there is a attack. I mean, and a lot of the cyber analysis functions which are being implemented are to detect attacks and then to basically deprioritize the data until you know what is the problem.
Right, thank you very much. We have one more question here, and the question is, with the increase in non-linearity in power system components and the fact that with the increased number of power electronic-based devices, sort of voltages and currents that we see in the power system are not as sinusoidal as they used to be 30, 40, 50 years ago. Is there any update on how power system engineers globally are adapting power system control and monitoring to cater for this new dynamic form of power system operation?
Okay, so I'll give you my grid level perspective. I'm not a harmonics expert, but I do know that these are introducing all kinds of new frequencies and harmonics into the grid, and they typically localize. Like it could be at a wind plant or a solar plant when you have inverters and you have. So, but from the grid level perspective, I really see the fact that the explosion of power electronic loads, for example, in the old days, loads gave you support during during emergencies, meaning when the voltage went down, a frequency went down, the load went down. But with power electronics loads, they do not go down, they're constant power. So from the grid operator's perspective, the proliferation of power electronics of the loads is not helping them. But in terms of at a location, like at a wind plant or a solar plant, or I know that we're coming up with smarter inverters, like renewables typically do not offer inertia and things like that to help you during the loads, and they introduce harmonics into the system. So I know that smart people are building smart inverters which provide you artificial inertia, and I think also to handle sort of mitigation of any harmonics which are being introduced due to the power electronic devices.
Thank you very much. We have one question here from Sivuyise, and the question is, what frameworks or models did you use to balance EMS objective investment decisions?
Okay, that is a loaded question, and I don't know how to specifically answer that. Now, what do you mean by balance objectives? Is there something you can clarify on that? Or because, like I said, the operations the objectives we began with were, I mean, the number one thing is you do not want to shed load. Okay, so every customer, that's the last thing a grid operator wants to do. Then beyond that, then you can have different levels of load shedding, by priority. So I don't know, and maybe if you could just rephrase the question so that, am I on the right path?
All right, so I would leave Sivuyise to send through a follow-up question on that so that we can respond to it. The next question here is from Shu Shil, and it says, excellent presentation, Dr. Giri. How much is the maximum spread of angle separation recorded by PMU under normal time?
Okay, that's an excellent question, because when you are measuring angle differences across, and this could be across any 2 points in the grid, okay, it doesn't have to be across a line. You can take a measurement in Cape Town and a measurement in Johannesburg, and that'll give you an indication of the grid stress between those 2 points. So it's any electrical connection between those two. Now, the thing is, unlike a transmission line, which says you can only have 50 megawatts going through it, or 100 megawatts or MVA, when you're looking at angles differences, you do not know what is a good angle difference and what is a bad angle difference. It all depends on grid conditions and the grid loading and the topology. So what you have to do is, if you have Cape Town and Johannesburg, and you want to know what is the bad angle difference between those two, you have to run model-based studies and try to stress the system and see when it breaks. So if it breaks at 90 degrees, then you know you want to keep it below 90 degrees. Or if it breaks at 120 degrees, then you want to keep it below 120. So that's an excellent question, because angle differences do not have a easy way to measure the limit. You don't know what is a good limit, good angle difference versus a bad angle. And the only way you can find that out is by running studies using models and then keeping that offline.
Thank you very much. See, we have quite a number of excellent questions coming through from our audience tonight, local time. We have one more question here from Gerald Brown. And the question is WASA systems. So I suspect WASA means wide area situational awareness systems, require very high performance communication. From your experience in developing large scale WASA systems, were utilities existing capable of handling this communication, or did they develop entirely new networks for these systems? If new systems were developed, what was the cost ratio for network infrastructure versus the grid infrastructure, i.e. PMUs, etc., for this project?
Okay, so I have to confess that I'm not a communications expert, and so I don't know what the costs involved are, but I know that what we can do is, when you're getting, like, say for India, for example, you're getting measurements from all across the country. Now, obviously, you don't want to get the 25 seconds samples per second coming into the control center from every substation. So what you do is you have different levels of filtering, meaning you have things called PDCs, phasor data concentrators, which allow you to have a hierarchy of communications, which allows you to bring in the fast measurements locally, and then send up the other measurements at a less frequent rate to the next level, and so on. So the national control center may be just getting one measurement per second from all the. So one way of controlling the cost on the communication system is to keep it more local, rather than having the entire grid having a very fast communication system. And the way you do that is by sort of decimating your measurements so that they don't go all the way at all the time. But on the other hand, the National Control Center may want to see what happened when you have a really bad disturbance. Then you can have the control center request, okay, all the hierarchy to send detailed measurements of what happened prior to the disturbance and after the disturbance on demand. So you can look at it in two ways. One, of getting measurements continuously around the clock for monitoring, and then getting measurements on demand to analyze a specific situation. But as far as costs go, I'm not the right person to answer that question.
All right. I think, but you've alluded to the matter to say there is a balance between very frequent data points coming in versus what you mentioned in your presentation, actionable information. So I think that's the balance, and that will speak to the amount of resources, financial resources that can be put towards this sort of project.
Correct. Yeah.
We have one more question from Anil, and the question says, in the recent Northern California blackouts, there was plenty of energy, but not enough time, or I guess transmission capacity. That's the question. Do you recall what really happened in that blackout?
No, I'm sorry. I don't know which blackout he's referring to, and but regardless, I mean, I really am not. I didn't study that blackout very much.
All right. So Anil, you're welcome to send a follow-up question.
And that's true, David. If anyone has questions, they could send it to you, and you can send them to me, and I will do my best to answer them, or even call upon some of my expert friends to provide some answers and get them all back to you. So you have my email address, and I'll be happy to. I'm retired, so I have plenty of time now, so I can try to help you guys as well as I can.
That's great. So I think we have 3 more questions here. The next one from Michael. In general, what do you think the level of disruption to grid management will be, especially to PMU strategies by SMRs, assuming they become a reality?
What are SMRs?
SMRs, Michael, tell us what SMRs are. But I think the general understanding, based on how the question has been put through here, is that at the moment there are grid management strategies that are in place, and PMUs are coming online to augment that based on your presentation. So are utilities around the world accommodating of this new disruption to the existing management regime as caused by PMUs? And is there enough interest on the ground to ensure that some of these existing strategies can be replaced by new PMU strategies, especially when it comes to control center operation?
Okay, that's an excellent question, because if you talk to grid operators, like I said, I mean, when we first told grid operators, we can show you oscillations on the grid. And the grid operators says, why do I need to know oscillations on the grid? So they really want to know what causes problems on the grid. So in many cases, a lot of grid operators are quite satisfied with what they have today. So when you start introducing new technology to them, and you start saying, PMUs can give you all this additional information, etc., it's like with any new technology, unless they see the benefits, it's more like adding to their workload. So they don't necessarily embrace it quickly. So one of the challenges is to provide training facilities, and this is something that we did at GE. And thanks to Pacific Gas and Electric, we created a dispatcher training simulator where we replaced the simulation engine with transient stability. So that allows you to simulate sub-second dynamics of the grid. So that allows you to now train operators offline on the benefits of PMUs. So once they see the benefits of, say, as something as simple as angle differences, if you can show them that if you measure angle differences between these 2 points and it suddenly changes, it gives you information, I think that then they will start accepting it more readily. So, but quite frankly, grid operators around the world have their hands full already, and they typically do not want to take on new technology unless it makes their job better. So it's up to us as the utility people or management to demonstrate using maybe simulators the benefits of these new technologies and to show them that it could make their jobs a little easier. So I think in many ways, right now, a lot of the PMU technologies are being handled by engineers at utilities, and in setting up scenarios and demonstrating, doing post-event analysis, which is much more effective at this. But in terms of bringing it into actual management of the grid, it's a training process, like any new technology. Like we had full graphics at one time. They said, no, I'm very happy with my character graphics. I don't need full graphics, until you show them that you can do a lot more with full graphics. So I think we're at the juncture now where it's up to us to demonstrate to the grid operator we can make their job easier, and with PMU technology.
Thank you for that response. We have a question here from Prof. Martin Kampa. With the future grid becoming more inverter-based, how do you see the stability of the grid in terms of grid strength, protection, etc.?
Yes, like I mentioned, with more inverter-based power electronic interfaces, and basically what you're having is the inverters are sort of interacting with the grid. So the development of smarter inverters, whether to provide better voltage control, like when you have a right through of a renewable plant connecting to the grid with the inverter, if you can show that you can provide voltage support when you need to, and also more importantly, as they grow, if you can show they can provide some inertial support, meaning through synthesized inertia, where a traditional generating plant has rotational inertia. And if you can develop smart inverters which can provide you some artificial synthetic inertia to prevent the frequency from sort of departing too far, that'll be a big help. So I really think with the growth of inverters on the grid and the increased focus on smarter inverters to help the grid, I think that'll make the case for adding more renewables and DC type of resources onto the grid a little more attractive.
Thank you. We have questions coming in numbers, so I think I would only take two more. We have one from Hilary here. And Hilary's question is around cloud computing, that what is the most significant added advantage that cloud computing has brought into power systems to enable power system monitoring and control? So that's okay.
Yes, so cloud computing, the nice thing about it is, and in fact, that's the world we're transitioning into. I mean, that's going to be one of the sustainable impacts of the post-pandemic, meaning that we're going to do more online stuff. But if I take like training, for example, I mean, when you have a big interconnection, you have multiple utilities, and sometimes you have to do joint training where each utility has to participate in doing the training. So what you could do is you could have a training simulator set up in the cloud, which is managed by, say, the transmission owner and or the grid owner, and then you have the different participants work on that remotely using their own communications into the central location. So the other good thing is, as you make changes to the simulator, you just do it in one place. So rather than having it in multiple places, you make the changes in one central location, and then everyone benefits from that. So the maintenance, the enhancements, and the new model can all be done in a central location and could be shared across a wider audience rather than each one having their own simulator. So the cloud-based computing and technologies allow you to centralize sort of your analytics and to share them across a much larger group of people.
Right. So thank you. This one that's on point, and the sort of decentralized computing will continue to play a role as we move into the next phase of power system advancement. And in line with that, we have a question here, which I think is very great for the academia. And the question from Alois is, any comments on necessary changes to power system syllabi in universities around the world to train electrical engineers of the future? Yeah.
Okay, so David, that question is for you. You're a professor, right?
Well, one of the significant changes that we have seen and we are working on at the moment is the fact that power systems are not as ideal as they used to be 60 years ago, 20 years ago, 30 years ago, with the increase in power electronics and harmonics that are injected into the network. So as a starting point, the fundamental assumption in a lot of undergraduate courses around balanced systems and systems with sinusoidal waves, I think that is becoming a thing of the past. So we need to train power system engineers to get used to non-linear power systems, and as well as the increased level of harmonics that we have to deal with. In addition to that, we have an increased level of imbalance in the power system. And so from revisiting theories that are based on assumptions that were true 20, 30 years ago, we need to understand how relevant are these assumptions and do they still hold, and develop new theories to cope with the challenges. So from an academic perspective, that is what we are doing at the moment. I'm involved in some of those initiatives, and I think that will set us on the right track to train power system engineers of the future.
Okay, from the grid operator's perspective, the more intelligence that is distributed across the grid is better, because in the old days, when you had a disturbance and it gets propagated across the grid, by the time it gets to the controls grid operator, is probably too late. So by making the distribution system more automated and intelligent, it's really helping the transmission system, because you can detect disturbances more quickly and contain them more. Like substation automation, for example. I mean, that is a big benefit to grid operators, because you make a substation intelligent and in the sense that it can take controls. I mean, you have to do, even if you do basic Kirchhoff's laws at substations to make sure that the measurements coming to the grid operator satisfy Kirchhoff's laws, that is a big help, because then you avoid sending a wrong measurement back to the control center. So I really think the more decentralized, distributed intelligence we have across the grid will make it a much more effective and reliable grid.
Thank you. So Michael, in conclusion, Michael sent a follow-up comment, and his SMR referred to small modular reactors.
Okay. Oh, okay.
So his question then is, in general, what do you think the level of disruption to grid management will be, especially to PME strategies by SMR, which are small modular reactors, assuming they become a reality?
Okay, so I would treat this like similar to other distributed generations or DERs, distributed energy resources. The SMR obviously is probably going to be a stable output compared to maybe some of the other distributed generation resources, which could be a wind plant or a solar plant. So I think in terms of disruption, SMRs will provide less disruption than the conventional distributed generation, because I think they can provide more reliable energy outputs at more predictable levels. And so I would just treat it as a more reliable distributed generator, and I would welcome that.
All right, so that's about it from the questions that we have The last one which I will take personally is the question around resilience improvement. Should it be in transmission level or distribution level? I think the different levels in the power system need to be revisited in terms of resiliency improvement, be it distribution, transmission, generation. So I don't think it's restricted to any level in the power system. So I would like to really thank everyone for joining us today. It's a pleasure hosting you on behalf of the SAIEE, that's the South African Institute of Electrical Engineers, our colleagues, SIGRE Southern Africa, the Southern Africa Power Pool, and this IEEE South Africa section. Would like to thank our keynote speaker for the great presentation, as well as the audience for the questions and the excellent interaction that we've had. Thank you very much, and we'll keep on bringing exciting webinars to your attention. Thanks,
David.
Have a good day. Thanks.
Thank you.